Now, the session, this afternoon session will be handled by Professor Amit Apte. He is a faculty in Department of Data Science, IISER Pune. Also, he is associated with ICTS. So let us welcome him. Amit, the floor is yours.
Thank you. I will walk very, very slowly. And I know, but I think I will need some blackboard space. I think, hopefully they will, yeah. Is that okay if yeah, okay. I think he said yes to me, so so far so good, yeah. Sorry, I'm just writing things that we need later. And okay, well, thanks a lot for the invitation, Kutti, and all the other organizers. It's a pleasure to be here to give talks after many years. But okay, many years. That's not really true. But anyway, before the pandemic, of course, I gave talks. But then the pandemic happened, and then I left. And then okay, so okay, that should be fine. Yeah. Okay. So dynamical systems will make an appearance today, but largely tomorrow. Today, I will basically talk about the conceptual framework in which ensemble Kalman filter and particle filter can be thought of as, so say, one single thing, and why it is essential to talk about ensembles in the first place. So I'll start with an introduction about why chaos necessitates all the things that I talk about, which is probabilistic framework. And in a way, something that I think wasn't discussed in great detail, so hopefully it will not be repetition and something new, which is talking about model errors and representativeness errors, the relation between the two, a different way of looking at what these errors imply and how they may be incorporated into data assimilation. I will not really talk about examples of this. Hopefully that will make an appearance next week much more significantly when you talk about real world applications. Okay, so this is a topic which is semi-independent. It's more like a background of data assimilation rather than a specific topic within. So you can sleep for 20 minutes, well, 10 minutes, whatever it takes to do that during that time. You need a nap after lunch, so that's why the break. Then the Bayesian formulation is the main crux of what the rest of the lectures will build upon, and that will lead towards talking about sampling of probability distributions, Monte Carlo techniques, and how that leads to ensemble Kalman filter and particle filter. So that's the plan for today. Details of ENKF that I don't finish today will be for tomorrow, and particle filter will be completely for tomorrow, including the hands-on. So I will send you a notebook, hopefully by today evening, if not before the lecture for tomorrow. And tomorrow it's 3 time slots. I'm going to hijack the afternoon hands-on time slot as well, most of it, at least. If you had other plans, please let me know and we can do something. And so I will not really keep the hands-on session only for hands-on, but start with working through some notebooks related to ensemble Kalman filter, Python. So IPython notebooks, so there will be IPython notebooks. Everything should be there. The only thing I realized may be needed will be JAX, but I'll upload this on Slack, and if it's a Colab notebook and you are able to browse, then anyway Colab will have all of that installed, and whatever else is required, I will upload that on Slack by today evening, once my notebook is actually working, which it's not currently. Okay, so IPython. So you have used IPython. All of you have used IPython notebooks? Yes, no? Okay, not everybody had said yes, and some of them specifically said no. The sum is not equal to the number of students, but that's okay. It might be more fun if there are teams of 2 or 3 people who work together through those notebooks, so that then if there are difficulties, you can solve those difficulties together. And how many of you have laptops on which you can run IPython? Notebooks, sorry, Jupyter notebooks. I guess Jupyter notebooks will be sufficient. Okay, so there is 1 or 2 people missing possibly. So all of you have that. So if you want, you can work alone, that's okay. But If 2 or 3 of you want to team up together, that might be good. I have.
The team members are not from the same institute.
I was coming to that. Preferably, not from the same institute is a requirement, and different genders would be useful. So don't mix up. Mix up in all possible ways that you can mix up. North India, South India, East, West, not the same institute, whatever it is. Okay. And bring the laptop for the whole day tomorrow, please. There are chargers here, so you should not be able to, you should be able to run the laptop for the whole day. There shouldn't be an issue with that, and so on. Yeah? Is that fine? Okay, good. So, repetition is, I guess, never hurtful. So let's go through that. What is data assimilation? Why data assimilation? And so on and so forth, right? Partly because here is my definition of data assimilation, and everybody has a definition, I think, and none of them match. So the way I think about data assimilation is what Varun already said. It's an estimation problem, estimating the state of a system, but it's a time-dependent problem, so repetitive in time. For what type of system? What is it that you have available with us? We have available partial and noisy observations. And as soon as you say a partial observation is something that's quite crucial in many cases. The observations are in fact quite sparse, 1 or 2 orders of magnitude less than the number of variables in the state. Noisy is redundant because observations are always noisy, but anyway. So we have observations and a dynamical system which is complex and high dimensional. That's a common application of data assimilation. Which of you are not working on or do not have any background in any topic of earth science, some topic of earth science? For example, you may be from biology or I don't know what else, something else completely. So who does not have any background in problems related to either ocean, atmosphere, ecology, or something else, and so on? Okay, so all of you have some background in earth science. I didn't look at the profiles completely, so I don't really know, but okay, so this is always the case for most earth science systems. These are complex, high-dimensional systems, chaotic. There are online people as well.
Yes.
Ah, yes. Okay, so online people, you can chime in. I'm not able to see you, and I hope you can see me. Actually, you don't need to see me. You can see this. That's good enough. And if you have questions, please just unmute. Can they unmute themselves and ask?
They can ask us.
They can ask. Okay, perfect. So ask questions in the middle. That's perfectly fine. The second part, which is what I will spend some time on, which is that the models that are available are always imperfect. There are things that are missing in the model, and we'll discuss what those things are and so on. And the model, the imperfection in the model is not just for the system dynamics, but also for the data noise. And I realized that I should do this. Okay, so I'll stand here and move the mouse here. So the imperfect models are both the data noise and the system dynamics are imperfect. And using all this, somehow combining all these ingredients, we want to get a state estimate. What does that mean? We basically want to, in most cases, prediction and associated uncertainty. So we want to deal with uncertainties, big word, as Varun said, but okay. So we will have to deal with that big word throughout these lectures. So state estimation problem, typical problems are estimation of, say, temperature, rainfall, this and that, and so on, over, let's say, something like weather timescales, tomorrow, day after tomorrow, this week, or even slightly longer medium-term timescales, months, or it could be climate timescales, but on climatic timescales using data assimilation is not quite a common thing, largely because climate is more of a boundary value problem rather than initial value problem. So these are, this is, the second part is not where, but it is a state, the second problem is also a state estimation problem, though not many data assimilation techniques necessarily get used there. So most of these, there are good physical theories, Navier-Stokes equation, thermodynamics, all of these we know very well. Combining them together into getting good models is usually the most difficult aspect. So models may not be as good as the theoretical framework that we have available for it. These systems are noisy, nonlinear, chaotic, nonlinear, usually deterministic, multiple scales in space and time, and observations are noisy, sparse, and discrete in time. Those are all of these characteristics, right? So where does chaos make an appearance in this? Here is an example that I think all of you must have seen somewhere, the chaotic system that was introduced by Lorentz in 1963. And there are two versions of this which are shown. The left-hand side just shows two initial conditions. One is there are two different colors, and two initially slightly separated trajectories. You can't see the separation in the initial condition here. And you can see that there are two colors visible, red and blue. Sorry, if there are some people who are colorblind, apologies for that. I should have used colors which were slightly better, but anyway, for now, this is it. And they look similar. They look almost identical, but they're not. If you look at the trajectory as a function of time, in this case, the x coordinate, you can see that for some time, they are visually almost identical. So the error is probably less than 10 to minus 2, 10 to minus 3 or something. But at some point, eventually, the differences between them become substantially large, that is visually visible. So in this case, essentially order 1. So at some point, the differences become large, even though the differences on this scale, you can't see the difference between the two trajectories. What does this mean? That there are differences here, but there are no differences on the left-hand side. Why is that the case? How is that consistent, or what's wrong? Is there something wrong, or is there a way to explain this? These two trajectories, you will say, they look almost the same, right? Very close. You don't see this difference, which is order 1 difference on this side, on the right-hand side, is not visible in the figure on the left-hand side. Why? Or explain what's happening. Any ideas? There's some hint about the two words on the top there. If you know those words, then maybe you can use those. Okay, so here are the two properties of these kind of chaotic systems. Almost every trajectory that you will look at, they look almost the same. That's the left-hand side. What do you mean by look almost the same? If you take any statistical average, if you compute the average of some quantity, say x, for example, the average of x in this case turns out to be very close to 0. I think it's 0 maybe, I forgot. And average of y is also in fact 0. Average of any quantity, any function of x, y, z, the 3 coordinates of the Lorentz system, turns out to be the same for almost all trajectories for sufficiently long trajectories. So that's what you see. What you see on the left is effectively a statistical picture, that is where all the trajectory goes over a long period of time. And it just stays on what is called attractor, that is that butterfly-shaped attractor. And so it looks the same, that is the statistical averages turn out to be the same. But on the other hand, the actual trajectories themselves, in fact, are vastly different. So that's what is seen on the right-hand side. The trajectory is different, but the statistical properties are the same. And that's what is meant by they are ergodic but chaotic. Chaos means that the trajectories diverge away from each other at an exponential rate, and you can't see the exponential on this side, but that will be part of the notebook, the hands-on exercises that we'll do. If you have done them before, then it might be a useful repetition. But on the other hand, if you compute any statistic, that turns out to be the same for almost all trajectories. And that is called ergodicity. So all of these systems are ergodic but chaotic. But because they are chaotic, if you want exactly trajectory information, if you want to follow the state of the Earth, which is one single trajectory, and not some statistical average over 25 different Earths, then you need to pay attention to the second point, which is that the trajectories diverge away from each other. Right? And so one of the consequences is that the predictions, if you try to do deterministic predictions, they become impossible over what I call the Lyapunov timescales. That is, essentially in this picture, the timescales over which the difference between the two trajectories start becoming visible in some sense, order 1 differences, right? And so that is of the order of a few days, maybe 7 days or 10 days for an atmospheric system. I actually do not know what it is for the ocean, and so on. So I don't know how many of you know this, which is that chaos was actually discovered when studying the dynamics of the solar system by Poincaré in 1880s or something like that. And he could not conclusively prove or disprove whether the solar system dynamics is chaotic or not chaotic. In fact, it took about 100 plus years until roughly the work that's cited here, it's I think 2005, 2010 or something around that time, that there was a conclusive evidence that in fact the solar system is chaotic on time scales which are of the order of millions of years. So the Lyapunov time scales, which is something like 7 days for the atmospheric dynamics, it's of the order of 10 million years or so for the solar system. So, okay, anyway, but it is chaotic. And if the deterministic predictions are not possible, the uncertainties that come into predictions play an important role, and hence probabilistic predictions are extremely useful. Yeah? And that's where we will eventually go. If we want to do predictions, we can't just find accurate representation at one given time and continuously do predictions forever. Very frequently, we need to keep correcting our predictions or estimation, and that requires frequent observations. Right? So that's this picture. The trajectory in the middle, somewhere, the red guy, is a representation of some true dynamics. We want to follow that. Because of chaotic nature, if you start with some initial condition, sets of initial conditions, those will diverge away from the truth. You have to find a method, which is data assimilation, to correct these so that to bring it closer to the truth, go forward in time, you again diverge, you bring it back closer to the truth, you keep doing it, and if you don't keep doing it, these trajectories will keep going farther and farther away, and the prediction errors will grow exponentially fast. So, okay, so that's what is data assimilation. So, why Bayesian formulation? Where do a more mathematical, conceptual and then mathematical description of where probability should play an important role. I'll not spend a long time here. I said this in the beginning. This is just kind of laying it out much more specifically. We have good scientific theories that describe the system. The models that are built based on those theories are not as accurate. Now that's a philosophically very fraught statement when I said this, which is a separate topic. I should have put that. Okay, so there is a reference to the difference between models and theories. And but the models that we have, for example, WRF model or whatever else, and so on and so forth, they are clearly not accurate enough, and there are things that are missing that people know what are missing, right? And if you are missing pieces in the model and the system is chaotic, combining both of those together, we need firstly accurate initial conditions because the uncertainties will grow at an exponential rate. And not only that, we then need observations, because if you don't have observations, then the system will eventually, on the Lyapunov time scale, diverge away from the truth. Right? So that's sort of say slightly broader. And then, if you're curious about the first relation between the theories and models, one of the books that has a provocative title, which is at the bottom. And, okay, so. Maybe let me skip this. I think this is not quite needed right now. Right. So the conceptual framework has essentially 3 pieces. What we have is an actual physical system that we want to study: atmosphere, ocean, whatever it is. We have a corresponding model for this system, an appropriate dynamical model that you have with you. And then there are the observations of that system. The observations are clearly related to the system. But of course, we also need to figure out a relation between the model that we have and observations. So there are these two relations. The relation of the observations of the system, the relation of the observations to the system, and the relation of the model representation to the observations need not be the same thing. I'll come to that in a mathematical term in just 5 minutes or so. So there is a potential mismatch between these two arrows. So there is a, okay, maybe I'll do this, which is the system dynamics. So now this was just the relation between systems and models and observations. The system itself is dynamic. The model has to be, of course, dynamic. But the system dynamics and the model dynamic are also usually different. So for example, if the model does not represent clouds properly, then on the time scale on which clouds are important, the system dynamics and the model dynamics will be quite distinct, for example, right? And so on and so forth. So there is also a mismatch between these two, right? And the mathematical representation of these two mismatches is actually what is called model error and observational errors respectively. And we'll see how to mathematically represent that. Yeah? That's the aim of next 5 to 10 minutes. Okay, so we need symbols to do to represent some mathematical objects. So WK will be the state of the true system, the actual observation, the actual Earth system. There is just no way that we can have any good handle on what that system is. We simply are unable to, even in principle, observe WK completely. That's just not possible. WKT would be a representation of that system into the model space. So if you are doing this with, let's say, a 1 kilometer resolution grid, then you have essentially a representation of, say, temperature, velocity, humidity, this, that, and so on and so forth at every 1 kilometer resolution. And that will be the representation or projection of the state of the system onto the model space. That is something that we are, at least in principle, available to us. But also it is unknown in the sense that we really don't know exactly what the true system is. And if we knew it, then we wouldn't be using data assimilation to do anything else. But right? Instead of that, what we do work with, you run a simulation, and whatever the output of the simulation happens to be, that will be represented by WD. So WKD, and K is the time. Did I mention that anywhere? It is there, TK. TK is the time. So K is the time, discrete time for now. And WKD is what you get out of simulation or assimilation or whatever actual practical implementation that you have. So 3 different objects. That is even in principle not available. WKT is at least in principle available. And WKD is what we really have that we can work with. And the difference between these 3 is where the model error and the representativeness error come from. Okay, so here is a picture. We are starting, this is a dynamical system. That means you go from time k to k plus 1, k plus 2. I'm going to talk about discrete time to make it easier. So the T, which is a superscript, is truth, though I don't like truth, but anyway, that's a philosophical topic. So WK is the system at time k, WK plus 1 at time k plus 1, and so on and so forth. We assume that there is some unknown dynamics that takes you from time k to k plus 1 and so on and so forth. So there is some dynamical system GK that we don't really know. What we have is a finite dimensional model space that we have available with us, actual simulation model space. And there is a true representation of the true system, again, that is not known, which is what we want to try to estimate. And for that we have a code that takes you from time k to k plus 1 and so on and so forth. So we know how to go from time k to time k plus 1. So take at least in principle, the system at time k, and go forward with the code that you have that goes to time k plus 1, and that is fk, the model f, applied to the system, the true system wkt. And that is not exactly the same as the representation of the true system in the model space at that time. There's a mismatch between the two. So here is the example. The true system contains clouds. The W's here all say contain cloud dynamics. WKT is a representation in a model that does not contain clouds at all. There's no representation of clouds in this model, suppose. So WKT has no way to represent clouds even. So WK, when it goes to WK plus 1, say the clouds have increased or decreased, or there is rain and hence the clouds disappeared. Something happened with the clouds in the true system. My system at time k did not even have clouds to represent. I take it forward with some dynamical system which cannot represent clouds. I get something which of course will not have clouds either, but whatever was the effect of clouds on the true system, the variables that I do have, say velocity and temperature, the effect of clouds on those variables will be completely missed in my dynamics of the model, but will be present in the representation of the true system into the model space. So this representation includes the effect of clouds, though this arrow has no idea about what to do with clouds. So the push forward, the going forward in time according to model is not the same as going forward in time of the system and then just projecting onto the variables that you have. So there's a mismatch between the two, and this mismatch is what is called a model error. Okay, of course, as I said, this is in theory, in principle. I don't have this exactly. I don't have a good representation of the system. What I do have is some, let's say, simulation. I took some reanalysis output, and that's my representation that I have at time tk. And I can apply the model equations to this, and I will get something else in time at time k plus 1 and so on. Of course, there is a mismatch between WKD and WKT, and coming as close to WKT is the aim of data assimilation eventually, repeatedly in time. So the model equation simulations are insufficient. That is, there is a error in representation of WKT when I'm actually doing my simulation. So the difference between this and that, the WKT and WKD, is what is typically called the initial condition error. The difference between the dynamics of the true system and the model dynamics is what is called a model error. Two completely different objects. Okay, so here's the mathematical representation. It is visible, kind of, hopefully. Okay, so if you start, so if I could go from the model system to the true system, essentially that I can represent everything in the system, then this projection operator that takes you from one to the other is invertible, which is actually not the case ever. But suppose it were invertible, then there is a nice way to write WK plus 1 true as a function of WK true, but it's not invertible and hence it cannot be done. So the idea is that the system representation at time k plus 1 is a projection of this, that's the pi, which itself is a time evolution of the system at time k, that's the gk. But what I have is the push forward or the model applied to WKT, and the difference between these two, which is just add and subtract the same term, gives you the model error. So the model error, as I said, the mathematical representation of model error is the difference between the projection of the true dynamics and the true dynamics on the projection. In words, in mathematical equations, it's basically this. Okay, so because we cannot represent everything in the model, the dynamics of the model is different than the dynamics of the system, and that difference, mathematically written here as delta, is called a model error, right? Okay, so this was the equation that I got at the end of all of that algebra, which is that for the true system, this dynamics will look like this. You go forward with the model, but there is an additional term that will be called a model error. Okay, so identical. So this was the mismatch between the dynamics. There's also a mismatch between the representation of the observations. So the actual observations, WKO, which are now the observations, of course are related to the true system. They are really coming from the true system. And there is some true observation operator, I call it HKC, which relates the observations to the true system. As opposed to, I have a model state space, and I want to project from the model space to the observation space. And that is the observation operator HK. H, in the K is the time, so H is the observation operator that I have used the same notation at least in this case. H is the observation operator. Why is there a difference between the two? If I'm observing, say, temperature at ICTS, that's WO, WKO. Now, for the true system, how do you relate the true system to the temperature at ICTS? Well, that's just the projection of the infinite dimensional atmospheric system to one-dimensional system, which is the temperature at ICTS. It's just that single projection. WKT, suppose, is a model with 10 kilometer resolution. There is no grid point at ICTS. So how do I get WO in my model? I could possibly do a linear interpolation with 4 nearest point to ICTS, and the HK will be a interpolation operator applied to those 4 nearest grid points. So HK is not the same as HKC. Those are different, right? And so the difference between the two, and mathematically then it's identical kind of algebra. You add and subtract the same term, and the observation is really related to the state of the true system, which I don't know. And hence I add and subtract the term that is coming from the true, the representation of the true system in the model space, which is the HK, the observation operator, the interpolation operator, for example, that I have, and then add and subtract the same operator, and whatever goes into this whole term is called the representativeness error. It's a difference between the relation of the observation to the true system and the relation of the observation to the model system. That mismatch is the representativeness error. Okay, so we have two equations. One that looks like this, which is that the model, the dynamics of the true system has that term delta, which was called the model error. The observations are related to the true system. The model representation of the true system also has additional errors. This is the representativeness error. This is the actual random error in the observations. And now the big jump. In almost all data simulation literature, some kind of assumption has to be made about the statistics of these terms. And the simplest assumption is that they are Gaussian. Why? Why not? I don't know. Because then you can do something. You can do some mathematics. Literally, that's pretty much the only reason. And understanding a better way to capture these representativeness errors is a big topic, and that's still far from being a satisfactory answer to how to deal with this actual representativeness errors. There are countably few papers on representativeness errors, and none of them are completely satisfactory yet. So there's a lot of things that can be done. Of course, everybody wants to use neural nets now to represent these errors. We'll see how good that comes out to be. But that's a place where now there is a huge jump. Assume that the model dynamical errors are Gaussian, and assume that the observational errors are also Gaussian, and then something can be done mathematically. If you already know some statistic, maybe not Gaussian, maybe not normal distributions, again, some things can be done, but things become more complicated. But we have to assume something about the random variables, which are these objects, the errors, model error and the representativeness error. Okay, so all of this was from this paper from 1997 of Kohn, and this, I didn't write down the full reference, I will add that maybe. That whole issue of the Journal of Meteorological Society of Japan has really nice articles on data assimilation, state of the art up to that time, 1997. And this is a very nice conceptual article. Okay, so this is what is called nonlinear filtering or the filtering problem. So here is a mathematical representation just to get everybody on the same page with the same notation. All of this has been covered by Varun, so I can go through this very quickly, I hope. And how much time do I have? Okay, 3. So I will do this. 0. Okay. Yeah. So dynamical model, go from time 2 to time t minus 1, and that will be represented by m. The model is always imperfect, as all models are. And yes.
Sir, you mentioned for a minute that there are few countable papers related to presentation.
Yeah.
So can you suggest best of them?
Okay, I can put in a, okay, so in the lecture notes, I can, the PDF, before I send it to ICTS, I will add the references to at least a couple of them. And there is a review paper recently, maybe 2-3 years ago, something like that. I forget the author names. So anyway, I'll have to look it up. I don't remember the actual reference right now, but yeah. Okay, so that's the representation of the model. Observations, you have seen all of this before. They are all local in time. And so it relates observations at time t to observations at time t. Sorry, the state at time t to observations at time t. That's approximation. Why? When you say that yt, the observation at time t, is a function of the state at time t, that's approximation. Why? What is approximate about it? Okay, so here is, let's say you are observing sea surface temperature from a satellite. So y is the sea surface temperature observation from the satellite. X is the actual sea surface temperature. Y is the observation. Why is this assumption that the observation at time t is a function of the state at time t? Why is that an approximation? Okay, I need you to speak. I'm not going to speak until you speak. So, go ahead, yeah.
Is it because they are indirect?
All measurements are indirect. But yes, that's part of it. And in particular, what does that have to do with time? Take that specific example. Y is the sea surface temperature observation of from the satellite. X is the actual sea surface temperature. Why is saying that? Okay, I want answers. There is nothing like a wrong answer. That does not exist. So whatever answer you give is perfectly okay. If you think you have a wrong answer in the mind, the likelihood that there are 10 other people who have wrong answers is actually the probability is equal to 1. And so don't think that, don't be shy. Answers, I need answers.
There will be some noise.
That's the eta. So the observational noise, instrument noise, that's eta. Not because of the no. My question is, why is it? I said the observation at time t is a function of the state at time t. Why is that approximation? Okay. How is satellite observing the sea surface temperature? Radiation. Okay. Keep going. Follow the chain of thought. Time delay between what and what? Yeah. So if it's passive or active, depending on which way it is, there is a time delay, which is the speed of light is finite. Okay, that sounds like trivial. So that's one approximation for sure, right? There is a time delay between what you think you're saying the time sea surface temperature at time t. Of course, there is a time delay of some fraction of a second. Maybe you can say that's negligible. How about, suppose the data assimilation cycle is, let's say, every 6 hours. So you're collecting observations over the 6-hour time window in order to be assimilated into the state at that time. So at 12 noon, you're assimilating observations from 6 a.m. to 12 noon. So a sea surface temperature observed at, say, 9 a.m. is still assumed to be, for example, the temperature at 12 noon. Now there is a 3-hour time difference between What the state was at 9 a.m., but you say, oh, this is observation at 12 noon, right? There are again very few papers that talk about how to try to make corrections in order to take that time delay into account. I know of only one or two. Maybe there are a few more, but not many. So okay, that's the approximation. All I'm trying to do is to make your thinking much more and more precise in terms of what is it that is assumed and what is it that's mathematically solid base, right? So all of this is assumption. There is approximation in making that assumption, and you have to be aware that that approximation may be consequential. So, okay, so that's the observation operator. There is of course noise. All observations are noisy, and we have to know, as we said, that could be coming from representativeness error or from the actual instrumental noise. Distinguishing between the two is very difficult, but I mean, I won't be able to actually show anything about that at all. I have not worked on it ever in my life. And so actually, I guess I said that in this point, and so I will go on. Right, the summary is here. I have observations up to time n. The notation match, which is amazing, between two lectures. We have observations up to time tn. Estimating the state at any time before that is called smoothing. Estimating the state at time tn is called filtering. Estimating the state at any future time is prediction, right? And in particular, in a probabilistic framework, which is what I will come to in a minute now, actually elaborating on how to build it up, we want the posterior distribution of the state conditioned on the observations that are given to us, and I will specifically focus on filtering problem, which means I want the estimate of the probability distribution of the state at time t. I should do this with a mouse. I want to study the state at time t, or the probability distribution of the state at time t, conditioned on observations up to time t. And I will think of finite observations, so time 1 to time t, finitely many observations. Right? So that is what is called a posterior distribution, right? And that was the other bit I was going to write there. The definition of, this is basically the definition of conditional distribution. This is the conditional distribution. In the notation there, x, A is the state, B is the observations. And this is what we want. And how do you get to this point? Through the Bayesian. So I guess you have seen the Bayes rule in the first day itself, yeah? So effectively we'll be using Bayes rule, but because it's time dependent, what Varun introduced in the last lecture, predict, update is the cycle that we'll come to. Okay. With a few more details, in particular now for probability distributions. So now we are interested in probability distributions of the state conditioned on the observations. The viewpoint shifts from looking at states to looking at probability distributions. That's the main object of interest. And so that's basically what I've written over there. Suppose you know the conditional distribution at time t minus 1, how do we get to the conditional distribution at time t? And if we can do that, then we can iterate and then keep going forward in time. Yeah? That's the cycle, the data assimilation cycle. So of course the first part is prediction. So you go from time t minus 1 to time t, that's the forecast or the prediction, and the forecast step or the predict step of the Kalman filter, for example. And what I have written down, essentially think of this as the model simulation, right? This is what you do with the dynamical model to go from time t minus 1 to time t. The derivation of this is straightforward. I'll leave this as an exercise, how prove that this equation is true. The only thing that you need to know is that the joint, so what do we mean by the probability of xt given xt minus 1, right? You need to know what is the definition of this, and everything else just follows in a straightforward way. You know how to compute the marginals. If I have P of A comma B, what is P of A? How do you get probability of A if you know the joint distribution of P of A comma B? if this is given, no? Joint distributions, you talked about joint, Vinit talked about joint distributions, right? First day you talked about joint probability distributions, conditional distributions, all of that. Yes? No? One yes. Two yes. Sorry? Sorry? So, say it again? Okay, these are not sets. I'm thinking of these as random variables, not as sets. All of this is in terms of random variables. So x is a random variable, y is a random variable, and so on and so forth. So a and b in this case are also, I could have been more, yeah, capital P is usually reserved for probability of sets. So let me write it as little p, so functions. So these are probability densities. Probability density as a function of a, probability density as a function of a and b, and so on. So not sets. Actually, for sets, this is not a useful notation. I'm not sure exactly what a set A, comma set B means. But so this is not set. These are random variables, A and B. P of, sorry, say it again. So you're just trying to divide this into that. Okay, fine. I want without using the conditional distribution. In terms of this, in terms of just this. Yeah, no conditional distribution. Even in the denominator also. Okay, do you know what is a, so if this is called a joint distribution, what is this called? Marginal. So that's a marginal. How do you get a marginal distribution given the joint distribution? You integrate, which is also sum. So if it's finite, then sum, otherwise it's integral. Or it could be in the finite case, this is sum over whatever the set B, if B takes finitely, actually it doesn't need to be finite, discretely many values, countable many values, then it's sum of over B of P of A comma B, right? I mean, these two things are the same thing. Integration, because it's a summation on a continuous space, summation is here. So if it's not, if it's continuous, then it's this. If it's discrete, then it's this, one of those two. This formula was written down, I'm sure, somewhere in that lecture. Has to be. Marginal is, okay, so if not, then it is, now you know it. And using this definition, using that definition, can you combine all of this and prove that this is the case? Yeah. But effectively, the interpretation is that this is the model dynamics. This is the evolution of the system in time to go from time t-1 to time t. The conditioning on observations, I did not emphasize this point yet. Okay, so the notation is when I say 1 colon t, that means observations from the time 1 to time t. All the observations up to that time. Yeah? Okay. So in this case, the right-hand side and the left-hand side both contain conditioning on observations only up to time t-1. I haven't yet used the observations at time t. That is the update step, or using the Bayes theorem essentially. And again, this is an exercise that is a straightforward, that follows straightforwardly. This is basically the Bayes theorem, the next step, which I have written down. The probability at time t, conditioned on observations up to time t, in terms of whatever we have until this now, which is, and this is called a forecast distribution, the PF. This is called the analysis distribution or update. So it's either PU or PA depending on the author. So the analysis and the forecast are related to each other by a multiplication by what is called a likelihood. Likelihood is the probability of the observations given the state. So I should have written it down. Oh yeah, it's here, likelihood. Yep. Okay, so it's all there. So P eta, which is the probability of observations given the state, is called likelihood. The product of the likelihood and the forecast is the analysis. That's Bayes' theorem. If you're not convinced that this is the Bayes' theorem, please explicitly write it down. And in particular, when you write it down, tell me what is the constant. So I said the analysis is proportional to the product of forecast and likelihood. What is that proportionality constant that I have left out? What is the expression for the proportionality constant? Yeah? Okay, so part of the homework, convince yourself that this is true. Part of the homework, convince yourself that this is also true, and in the process, find the proportionality constant. So 2 exercises, yeah? Okay, so you can put it all together. This is just because the forecast probability distribution is written over here, I just combine the 2 and this is the full thing, yeah? The first part of it in the square parentheses is the prediction or the model dynamics. The second part of it outside the parentheses is the likelihood using Bayes' theorem. Okay, so that's the viewpoint of data assimilation in terms of probability distributions. Just a picture. Effectively, you start with if you have something at time t, the prediction takes you at time t plus 1, but still conditioning on the observations up to only previous time step. Then you update. Now you are conditioned actually use the observations at that time t, and this thing can continue forever. So forecast, this is also called background. The forecast is also in data assimilation literature called background. And the forecast or the background is updated using the Bayes' theorem in order to get either what is called analysis or update. Okay. Questions? Okay. Kalman filter, just very quickly, because this was done just today morning. This is largely to set the same notation that I will use in the rest of the lecture. So I will go through it very, very quickly. If everything is linear and Gaussian, so let me just go back. If the model used for prediction and the update or the observation operator that goes into the update step, if both are linear, in that case, everything can be represented in terms of the mean and the covariance of Gaussian distributions. So all of these distributions that you see over here turn out to be Gaussian. And this is a property that I'm not going to prove, that if you have a Gaussian distribution with a linear dynamics, you continue to get Gaussian distribution. And if you have a Gaussian distribution at, say, the background time, then after the update, after the analysis, the distribution is still Gaussian. This proof is left out from this completely. So I'm just stating it as a fact that all of these are Gaussian, and hence what you need to deal with is the mean and the covariance. Using Bayes' theorem and using basically this update rule, the update rule the prediction rule which I wrote down in the previous slide. It's maybe a 5-page calculation roughly or something like that, of the order of 5-page calculation. You can compute the mean and covariances of all the Gaussian distributions, which are the forecast and analysis Gaussian distributions. And that computation gives you identical formula to what you get by trying to minimize the variance, which is what Varun did in the morning. So what we did in the morning, which is minimization of certain thing related to variance, is actually identical to the forecast and update of probability distributions. And that's a deep fact. That's not something that's obvious at all. And in fact, this is true only for Gaussian distributions. This is not at all true for things that are not Gaussian. So that is something I'm not going to prove, but the formula remains identical even if you go through the probabilistic way instead of looking at the variational way of looking at Kalman filter. And both give the same identical answer eventually. Okay, so since the update step and the Kalman, the prediction step are the same, I will not spend time on reading through these equations, but we will spend quite a lot more time on these equations, especially the update equation for the variance, just 1 minute, when talking about the ensemble Kalman filter later.
Both
Yeah.
the approach, least square approach and Bayesian approach, both are providing the same formulas.
The formula turns out to be the same. Yes, the formula coming from the variational approach of deriving the Kalman filter and the probabilistic approach give you the same formula. Yes, that is true. Which adds, I hope it should be true, because if it's not true, then you have two different things called a Kalman filter, which is then very unsettling. But anyway.
Initially, if I am starting to work on data simulation,
Yeah.
so I can't have command on both the methods. So what was the advancement of one over other? Is there any?
Can I answer the question after we talk about what are the pitfalls and where do what? One which is very immediate, which is what Varun also talked about, is that look at the Kalman filter. It deals with covariance matrices. If you have a million-dimensional system, the covariance matrix is a million cross million symmetric matrix. There's simply no way in the world that you can even store such a matrix, let alone do any operations on it. So that is simply out of question, even now. In Kalman's time, clearly it was out of question. Even now it's out of question, effectively. And so that's one thing, that you simply cannot deal with this as is. So new methods have to be developed in order to implement something that will be like a Kalman filter, but approximation of it with usage of memory and computation, which is actually feasible. And so even though Kalman filter was 1958, you said. I actually forgot that paper, the 1950 something, anyway, 1950s. Kalman filter was not 1940, it was 19, anyway, I forgot, anyway, let's say 1960 plus minus 10 years. The actual implementation of anything like a Kalman filter, which is actually the first time was ensemble Kalman filter, for large-scale atmospheric oceanic systems was early 2000, late 90s to early 2000s. And that's mainly because you cannot implement this as things that are written over here. There were things that were called square root filters, which can deal with slightly smaller dimensional systems, but even those are big enough that square root filters are not easy to implement either. And we will talk about square root filters later. But implementation of this was simply impossible, effectively. And hence, almost everything was variational, because at least there was no problem with the memory as much as it exists here. Computation was still a problem, but then you could deal with the computational problem at least. The memory problem was impossible to get around at all. There was just no way to represent this, right? So, okay, so the ensemble Kalman filter is a Monte Carlo representation, but coming up with the algorithm to deal with it, for reasons which I don't understand fully, well, actually, I do, in the sense that once you see it, it's obvious. But that's usually the case for most nice ideas. The most important ideas in science have that quality, that after they have been discovered, everybody says, that's very obvious. Okay, so I will talk about the ensemble Kalman filter in just a few slides. Yeah? In the probabilistic framework, it's not exactly clear what is it that you're after when you are trying to do data assimilation. So what we want is probability distributions. What do we want probability distributions to represent? Of course, we want to get some handle on the uncertainty. And probability is the natural language to deal with uncertainty. So that's clear, right? So here is another picture of this kind of method. So you have the distribution, the representation of the probability distribution at time, let's say n minus, I'm switching between k and t and n, anyway, it doesn't matter. So at time n minus 1, you go forward in time, model forecast, to time n, you have some observation at time n, you combine the two, you get the analysis or the update at time n. So everything inside this box is happening at the same time, Tn. There is a forecast, the observations combine them to get this, that's the Kalman update, for example, right? So all of this is happening at time n and this continues sequential in time. So what do we want? of course, if you want to keep using observations, maybe one of the things that we would want to aim for is whether the uncertainty of the state estimate becomes smaller and smaller and smaller or not. Is there a limit? Can we make the uncertainty go to 0? So we would like to think about how uncertainty plays out. Does it decrease? If the uncertainty increases in time with the data assimilation method that you're using, then probably it's not a very useful thing. Okay, so in terms of thinking of probability distributions, if you have a very broad distribution that's highly uncertain compared to a narrow distribution that's less uncertain, right? And so we may have something that is shrinking in time in some sense, right? Does it move closer towards the true system? Because we are trying to observe the ocean and atmosphere and so on. We really want to represent that system. If we have very high precision, but something that is far away from what the true atmosphere is, then that's no good either. So there is a distinction between how close you are to the true system and how precise you are. So the first, which is reducing uncertainty, is increasing precision, as opposed to coming closer and closer to the true system, which is becoming more and more accurate. The other thing is, which I will talk about hopefully tomorrow, I hope I get some time, to talk about stability of these things. It should not so happen that you start with two different initial conditions of the distribution, two different distributions, and you get two very different answers in time. So if the European Center runs a system with a initial condition, with an initial ensemble, and if NCMRWF in Delhi runs another system with a different ensemble, and if they don't give you the same answer or similar answers, then the system is not stable. They diverge in time in some sense, and that shouldn't happen. So stability, precision, accuracy, stability, all of those are desirable properties of data assimilation system, and probabilistic description makes all this possible to even talk about these. So here this is a picture from Wikipedia, by the way. If you have the probability distribution shown here, right? This is some Gaussian looking distribution, and the true value or the reference value is the line on the left hand side. That is what we are trying to capture through a probability distribution. And if this is the probability distribution, a reasonable estimate obtained from this distribution may be, let's say, the mean or the mode. In this case, the mean and the mode are the same, and this will be, let's say, our estimate of that quantity. The difference between the reference value, the true value that we were after, and our estimate of it is the accuracy, how accurate you are. And the uncertainty, which is kind of like, let's say, 1 sigma, 2 sigma of the distribution, is the precision. So in this case, you can see that the accuracy is terrible, because terrible with respect to what? With respect to precision. The true value is way, way, way outside the bulk of the probability distribution. This shouldn't happen. And actually, this is what is called filter divergence. Basically, when the filter starts becoming, so think of this as, say, the forecast or the analysis distribution for temperature, and the temperature is at 45 degrees Celsius, but the true temperature happens to be at 35 degrees Celsius. The uncertainty is maybe plus minus 3 or 4 degrees Celsius. So you would have a range of temperatures that you would give as 42 to 48. That's this value here. The true temperature is 35. So you have highly precise but extremely inaccurate prediction. And this is basically the core of what happens when there is filter divergence. The filter starts becoming more and more sure of itself. It thinks the filter is very precise, but highly inaccurate, and that is typically the manifestation of filter divergence. So that's, and this is also, by the way, called bias, right? The difference between, so the bias is high bias, high precision is a terrible place to be in, never should not be. So if, for example, compared to this, if I had a distribution that looked very broad, so that the precision is less, that would actually be preferable because at least the truth has a finite probability. Under this distribution, the truth has 0 probability. And that's filter divergence. Yeah? Okay, so let's keep that in mind. Okay, so we want the balance between precision and accuracy to be maintained. Yes. The precision is the inverse of the uncertainty, essentially, or inverse of the covariance matrix is what gives you precision. Accuracy is the difference between the true value and the estimate. Of course, that is only known a posteriori. That is, you can't know this a priori, right? Of course, we don't know the true value, and hence we are doing assimilation. So we would know how badly biased the system is. It will happen only after the fact. So tomorrow, I will know how biased today's predictions were after having observed today, and then doing some calculations. Okay, bias calculation is not easy, not difficult. You do a subtraction. But so the bias is known after the fact in some sense. Precision is a product of the assimilation system itself. And that's why I mentioned, remember my definition of data assimilation included that I want estimates, the state estimates, predictions, along with some estimate of the uncertainty, which usually is in terms of covariance or the inverse of the precision. Yeah, so some other possible questions. How about what kind of observations we should choose? Or if we make our observations more and more precise, if I invest 10 million rupees into getting a more precise instrument, if you change the precision of the observation, that is uncertainty in the observations is going down, does it lead to more precise and more accurate state estimates? Does your data assimilation system become better in some sense if the observations become better in the sense that they are more precise? That's not obvious, by the way. There are limits to what can be done. Choices between observation operator. This is called system design, observation system design. If you have one observation, one set of observations, let's represent them by observation operator H1 versus observation operator H2. Which one of those two will lead to reduced precision? Sorry, increase precision, and that will be preferable. You may not want to reduce precision. Okay, so these are some other kind of questions that you can try to answer from assimilation, right? There's a slightly subtle difference between trying to estimate better and better the state as opposed to trying to estimate better and better the probability distributions. I will not really belabor this point much. If we have some numerical scheme of approximating the analysis, so analysis is, this was the ideal representation of the probability distribution of the state. We have a numerical approximation, let's call it P hat. How good is the numerical approximation of the probability distribution, let's say using an ensemble, of the true distribution, and so on and so forth. So all of these objects are important. This is where the curse of dimensionality comes in. For high dimensional systems, approximating the probability distribution becomes extremely difficult, and that is called the curse of dimensionality. So, okay, so Monte Carlo techniques, right? We want to deal with probability distributions. We cannot represent them because they are just too high dimensional. For example, we cannot even store the covariance matrix. So what do? You deal with sample. What is sampling? Sampling is a finite set that represents a given random variable. So if X is a random variable which has a probability density G of X, sorry, I'm calling the probability density of f of X. So f of X is a probability density for a random variable X, let's say the temperature. The way to represent a probability density is in terms of samples. So I have capital N different measurements or capital N different representations of that random variable, such that, at least in theory, each of those has the same distribution as the original distribution, as the original random variable of interest. So we want some method by which x1, x2, x3, all the way up to xn have the same probability density as the original probability density of interest. Of course, if you don't know the probability density of interest, then that's difficult to do. So we have to assume that we know the probability density of interest and hence obtain these samples, right? So getting n such representations is what is called sampling. So if you have ever dealt with histograms, how many of you have plotted a histogram before? Histogram of any quantity, some quantity, somewhere in your life. Can you raise your hands a little bit? I think they feed you quite well, I know that, for sure. So please raise your hand. Okay, I think everybody. Did I miss somebody? Anybody who has never plotted a histogram ever in your life? No, everybody has. Okay, so when you are plotting histograms, what is it that you're doing? You have basically n numbers, and you are trying to find bins and finding how many of those n numbers belong to a given bin. What does that mean? So a histogram represents the following object. So if this is my histogram, now I'm getting bored of drawing histogram, so that's it. 4 bins. What does this histogram represent? So let's call this quantity x, and this is, say the midpoint of this is x1, or let's say xa, xb, or something, dot, 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 right? And this value, what does this histogram represent? And I had a sample of size n, let's call that x1, x2, up to xn, and I'm plotting the histogram with respect to the absolute numbers, that is, the sum of all of these bins is equal to n. Let's say that is my histogram. And there are n1 here, so na points here, nb points here, and so on and so forth. Right? And na plus nb plus n, whatever c plus nd is equal to the total size n. So what does this represent? The procedure is clear. You count the number of these data points, sample points, in this bin, and you plot that, right? That's what, so this value is NA, oh, sorry, this value is NA, this value is NB. But what does it represent when I'm talking about probability densities? This histogram is supposed to represent some probability distribution, let's say f of x. What is the relation between this and the plot that you see as a histogram?
Representing the probability distribution of the particular members falling under the particular bins.
Okay, yeah, so that's just the counting, yes. So the number of points is represent, for example, what's the relation between, say, NB and f of x? So suppose you had normalized this, so you do this, that's the normalization, right? When you plot a normalized histogram, what happens? The sum of all of these bins, the areas of all of these bins, add up to 1, right? Okay, so now you said that this normalized value is what? Will approach to, so approach means what? Under what condition? Approach under what condition? To what? Okay, approach under what condition? So 2 questions. Approach, you have to take a limit. Limit what goes to what gives you this. That's one question. The second, if I don't want to take any limit at all, just a finite sample, finite bin histogram, what is this supposed to represent? Again, that there is an approximation, clearly, but that bin size, the bin area has a approximate representation in terms of f of x. The bin goes from some left limit to some right limit. If there was a true distribution, the f of x is hopefully something close by, like this. This is a probability density should go to 0. So this is a probability density f of x. So now what's the relation supposed to be? The area under the curve for the true distribution is is approximated by the area of the bin, right? So this area is equal to the area of the bin, or approximately equal to the area of the bin. So what is it that we are basically trying to compute? We are trying to compute the average of a specific, sorry, go ahead. No, go ahead, yeah. So you're taking the integral. So this is equal to the integral of 1 going from a, so I guess the xl to xr, the left limit and the right limit. So xl to xr of the function 1 with respect to this probability distribution. It's an average, it's an expected value of the function that takes a value 1 between xl and xr and takes a value 0 outside everywhere. So that's a function of x, clearly, right? So this function I could have actually written as in what is called indicator function, that whether you belong to the set xl to xr or not. So I could simply then now do this. So this is a way, mathematical way of writing a function that takes value 1 in a certain region and takes a value 0 outside a certain region. In this case, this indicator function is from, say, xl to xr. That is, it's 1 between xl to xr and 0 outside that region. So it's an average of a specific function. So histogram really represents averages of, in this case, how many functions? 4 functions. A function that's 1 in this region, a function that's 1 here, a function that's 1 here, and a function that's 1 over here. So it's 4 averages of 4 different functions that are graphically represented in a histogram. And that approximate, essentially, not actually just the value of f of x. The better way to say it is the area. And of course, as the bin size, now this comes in, as the bin size goes to 0, the area is equal to, so this is not actually equal to f of xb, but multiplied by the bin size. So there was something missing, which we now discovered. This should approach this multiplied by, let's say, the delta, and the delta is the, this is the bin, as delta goes to 0. Okay, so why this whole discussion about what exactly is a histogram? You have plotted it, so you know what it is, or you thought you know what it is. I hope some of you at least knew exactly what that was. But anyway, so histograms represent areas as averages of specific functions, which are basically 1 in a certain region, 0 outside that region, with respect to the probability density of interest. That's what a histogram means. In general, for any sample, we can compute averages of some functions, whatever the function may be, using the sample that we have. So suppose g of x is a function of the variable x. In that case that I showed, it was the indicator function, the function that is 1 within the interval. But it could be any of, you could take a sine x, cosine x, whatever it is that you want. So given any function, the sample mean, the sample approximation of the average with respect to f of x is simply defined as this object. So the exercise is obvious. Now, given this definition, try to figure out why that turns out to be NA by NB. Sorry, NA by B and NB by N and so on. So how does this expression for functions that are 1 between the 2 limits of the histogram turn out to give you the expression that's over there, which is the number of data points within that bin divided by the sample size. Relating this to that is part of the exercise. Yeah? Okay, so the expected value, so this is the sample mean. It's an estimate of the value of the function g of x using the sample x1 through xn. Yeah, clear? So these are random variables, x1 through xn, and hence this is also a random variable. This is also called estimator, which is what Varun, the word that he introduced in the morning, is basically a function of the sample is called a estimator. So this is a random variable, that's an estimator. The expected value, you know this result, right? Expected value of the sum is the sum of expected values. No. 1 yes, 2 yes, 3 yes, 4. More and more nods. The expected, okay, firstly, you know how to compute expected values. If you are a bit confused by expected value, mean, and average are all interchangeable words, I think. Yes, pretty much sure. So you know at least mean or you know average with respect to a probability distribution, and that is called expected value. So I'll keep using the word expected value. What that means is simply the mean or the average with respect to a certain distribution. Yeah? So the expected value of this random variable, which is a sum of all of these. Now, expected value of the sum is the sum of expected values. And because these, now here is the additional assumption which I didn't emphasize. If they're identically distributed, that is all of them follow the same probability distribution f of x, the expected values are going to be the same as the expected value of f of x. And hence, the expected values of all of these random variables are the same. The sum divided by n gives you the same value, which is the expected value of the original function g of x. And so this is what is called an unbiased estimator of, so if the sample has this property that they are all identically distributed, you don't even need independence in this case, then it is an unbiased estimator. These kind of estimators are always unbiased. Just the sample mean is an unbiased estimator. Okay, that's a result that's very general. In addition, if they're also independent, then we can compute a variance easily. To compute a variance of a sum, so did you see this result in the first class? I'm not very sure. That variance of a random variable, let's say z1, or variance of a sum is not always equal to the sum of variances, but it is the case when, under what condition? So this is not always equal to the variance of z1 plus variance of z2, but it is equal, that is the variance of the sum is equal to the sum of the variances when, and what happens? What's the formula for the variance of the sum? Was it done? This was, I'm 99.9% sure this must have been written in the first lecture. Was it written down in the first lecture? Okay, if it was, then look up your notes. And it was in the lecture, it was on his slides as well. and if,
You remember the guy from online asked this question?
so first, two-part question. What's the formula? Suppose I want to write this is equal to that plus that. I said they're not equal, so that means something is missing. So plus what? Twice of what? Okay, so she says it's minus. Is it minus or is it plus? Minus, plus, minus. Somebody says plus, somebody says minus. Okay, so I will say plus minus and fix it. Find it, find what it is. If you haven't done it, if you haven't done this calculation ever, then you definitely should. And in particular, you definitely should do this calculation for not just scalars, but vectors. So Z1 can be a vector, Z2 can be a vector, and this formula would still be valid. In what way will it be valid? Okay, I'll leave it to you to deal with all of these problems. Fine. Anyway, so under what conditions are they the same then? the sum of variances as the variance of the sum. If the covariance equal to 0, and that is the definition of independence, independent random variables. Is it? Is that the definition of independent random variables? No, it is not. If they are independent, then the covariance is 0. You said that in the morning also. So, okay, in that case, this is true because a sample, I said that suppose the sample is independent, then the variance of this sum is equal to the sum of the variances. Because they are identically distributed, the variances are all equal. So n multiplied by the variance of the original random variable. So one of the capital N cancels. So 1 over n square times n times something. And so you get 1 over n times the variance of G. So when you take n to be larger and larger, the expected value does not change, but the variance keeps decreasing. And that's the reason for choosing larger sample size. It decreases the uncertainty of the estimates, always. So variance is a representation of the uncertainty, right? Okay, so this is what that I wrote down. And basically, I'm dealing with continuous distributions in this case. So what we want to compute is basically this integral of g of x, f of x, dx. That's the expected value of g of x. And that's approximated by the sample mean. Yeah? And the justification is to law of large numbers, which is stated here as n goes to infinity. The probability that the sample mean is actually equal to the true mean or expected value is equal to 1. So with probability 1, you will get the true value as n becomes larger and larger, right? Okay, so how about error? How far are we for a given sample size? And that is what is called the Chebyshev inequality. So the way to read this is as follows. I have Gn, which is the sample mean. The sample mean is what you can compute with a finite sample that you have in your hand. Expected value of Gn is what you want to compute. This is also the expected value of the true random variable because it's an unbiased estimate. So this is what you want to compute. This is what you can compute. The difference between what you are trying to compute and the actual value that you get from a finite sample is, of course, a quantity of interest, and that's maybe, let's call that an error. So the probability that the error is larger than a certain quantity is less than something. So the probability that the error, that the sample mean and the exact mean differ by no less than, the error is larger than, in this case, the square root of g divided by, the variance of g divided by delta is no more than delta. So for example, if you take delta to be very, very small, what happens? So you want the probability that you deviate from something to be very, very small. So take delta to be tiny. If delta is very small, what happens to this quantity? As you make delta smaller and smaller, what happens to this quantity inside the square root? That becomes larger and larger. That means that the bound that you put on the error becomes larger and larger. And that's obvious, right? The probability that the error is very large is clearly going to be small. But if you want the error to be small, then the corresponding probability has to become large. So there's a balance between the error, the bound on the error that you make, that you are trying to get, and the probability of making that error. You can't have both. You can't make very, very small errors with very, very high probability. So that's the problem, right? And so you can decrease the error by a couple of ways. In this case, of course, the delta is something that you have no control over. Right? The error that you're making, if you make delta small, then this can become small. The probability of making the error becomes small, but the bound on the error becomes large. If you make the bound on the error small, then the probability of making the error becomes large. Okay, so you can't have everything. So delta is not really in our hand. That is decided by Chebyshev. What is in our hand is capital N, As capital N increases, the error becomes smaller and smaller as 1 over square root of n. And as variance of g of x decreases, the errors also become small. So if you have a function for which the variance is small already, then that function can be estimated with higher accuracy than a function that does not have. Okay, I have 5 minutes to talk about. Okay, so ensemble Kalman filter in 5 minutes. That's my challenge. I don't know. I don't think I can do that. So all of this so most of this will be in some notebook, and I will skip the importance sampling because this is important for particle filter, which I'm not coming to until much later. So I'll come back to importance sampling later. And just to relate this to ensemble Kalman filter, remember that formula that the prediction update step. The idea behind ensemble Kalman filter and also the particle filter in the same framework is that instead of representing probability distributions in terms of, say, functions, you represent the probability distributions in terms of sample, and a sample will then give you appropriate quantities, statistic of interest, in terms of sample means. That's what we looked at, right? If you have a sample, then sample mean is unbiased estimator, and the variance can be decreased by appropriate quantities, for example, increasing the sample size or changing the function of interest and so on and so forth. So the ensemble Kalman filter is essentially the Kalman filter formula. At least you can kind of relate, hopefully you remember what the formula looked like, visually at least. And it's identical to the Kalman filter formula, except that you apply it to every member of the ensemble. So if you have a big ensemble, you apply Kalman filter to every member of the ensemble, and hence get around the problem of having to deal with very large covariance matrices. Because now you're not dealing with the covariance matrix at all. You're only dealing with applying this formula to each ensemble member and not using the covariance matrix. That's where the ensemble Kalman filter comes in. So it combines, so the probabilistic framework was the basis. We can't deal with it because we cannot store the matrices of interest, covariances, and so on. Sampling is the answer to getting around the problem of having to deal with covariance matrices. And the solution proposed was just use the Kalman filter, but for each ensemble member. And why does this work is what I guess we'll see the next time. So I guess I've at least introduced what is the ensemble Kalman filter, but why this works, and then illustrating this on, say, a specific system like the Lorentz 96 or something is what we'll do tomorrow. So most likely tomorrow morning I'll spend at least the first lecture on ensemble Kalman filter and illustration using a Jupyter notebook, and then start talking about particle filter, its theory, and the implementation of it in the afternoon. Yeah, is that sounds good? Yes? Okay. Feedback about the pace. That is, should I just go very fast, much faster, and go through the sampling and this and that and so on at a faster rate? Or is this something reasonably okay as of now? Are you all aware of, I mean, if you already knew everything about sampling, then I didn't need to do this, but.
Sir, this is very identical to Kalman filter.
It looks identical, yes, I agree.
And now instead of using one deterministic forecast, we have to use many forecasts at a time.
The ensemble, yeah.
So how we will generate the covariance error?
We'll come to that. I haven't written down the formulae.
And one thing, sir,
Yeah.
are there any methods? No. There will be many methods. How to create the initial ensemble?
Okay, so a few questions. One, initial ensemble. That's a question that we will come to later. Hopefully, I'll get time to talk about the stability problem, in which case the choice of initial ensemble becomes irrelevant, because after sufficiently long time, independent of what the initial ensemble is, they all start giving you the same answer, and hence the initial ensemble choice does not matter. And usually that is what is done. If you want, let's say, the predictions starting from you want reanalysis for starting from 1950, then you should initialize the system, let's say, for 1920 or something like that, Actually, you don't even need that far away, but 2-3 years, 5 years might be sufficient. The initial ensemble for the time t equal to 0, which maybe say 1945, will not matter for a reanalysis for 1950 onwards. And that's why you need stability. So the stability of this kind of data assimilation system, ensemble Kalman filter, is important. Is an important characteristic to have in mind. If they are stable, then the initial ensemble does not matter. And so choose something that's reasonable, which is, let's say, some Gaussian ensemble or something like that, and then it works fine. If we are on a much, much shorter time scale, you are choosing initial ensemble, but making predictions within a time scale such that things have not become stable, that is, they don't come back to the same system, then, of course, the choice of initial ensemble is extremely important. And I'm not sure if I will have time to discuss the details of how to choose that. Hopefully next week. See, I'm pushing something to the next week, but yeah. It's very important. Yeah, exactly. Yeah. And the second part of that was the covariances. How do you represent covariances and so on and so forth? So that will come to later. Yeah. The main idea is that you never really want to compute covariance of the full state ever, because what will you do with that information? This tells you if you want covariance between specific variables, then the formula is simply the sample covariance. The sample covariance is basically a function of the state. And hence, you can compute, say, the covariance between temperature here and temperature in Delhi from an ensemble. That's possible. So those formulae are what is the formula. G is the covariance. And you substitute here, and that's it. That's literally the formula for, yeah? Okay. Okay, sorry, I went over 5 minutes.
Thank you. Okay.